Hello guys, I welcome you to my channel Notabene Tech on Tube. Obviously we are dealing the courses related to aerodynamics, flight dynamic structures, and for continuation of those videos I have actually want to do another video preceding to the previous one. Actually I have covered boundary layer with the properties and explanation, the definition and the properties, and I've mentioned in the last video as well that I'm going to cover the boundary layer equations. So right now I'm just covering the equation. I have worked out the theory along with the equations in the notes, so that is why I'll just explaining it so that we can draw a conclusion that how we can handle boundary layer equations, how we can solve them out when there is any problem related to the boundary layer equations from any book, from any part, or from any course, or especially related to the aerodynamics. But boundary layer equations, obviously 2D steady flow is our course of study so far in aerodynamics, fundamentals of aerodynamics, and for the non-dimensionalized form of x momentum. Okay, if you have to see that we are going to cover around about four equations. One is about continuity, other is x momentum, another is y momentum, and the last equation is of energy. So these equations will form the basis of the boundary layer equations, and the whole concept of a boundary layer will going to revolve around these four equations. But to get or reach a point for those equations, we normally have to pass through a certain theoretical phase so that we can explain how we're going to reach those equations. So that is why this is the whole process. The concept of the boundary layer I've explained earlier with the properties, and right now with the help of equations, normally in the form of the derivative, and normally when we're talking about the x momentum, you need to talk about the rho and the density and also the velocity. And we're going to talk about the velocity, we're going to talk about the velocity u, we're going to talk about the velocity y, but obviously the velocity then will be in the form of x momentum. Okay, so here it is in front of you with rho dash or rho prime or u prime is equal to derivative of u prime into derivative of x and dx plus rho prime, velocity of prime, derivative of u and over derivative of y prime. So is equal to 1 minus 1 over r m infinity of square derivative of yet again rho into derivative of x, and then we have to plus 1 over r, which are real numbers, infinity rho derivative of y, and taking it under velocity u, and also taking it under the mu prime, and yet again taking the derivative in terms of x and y of v and u as well. So we have to reduce this equation, whole sort of the non-dimensionalized form of x momentum, and reduce it to approximate form. That is our because normally we're talking about the boundary layer. We have earlier talked about when we talked about the Newtonian sine form or sine squared law. We also discussed about the approximation technique. So this we have to deal the same boundary layer and under the approximation techniques, and to get the approximate form we have to see that the boundary layer is less than the scale of the body. This whole, for example, this is x, which is velocity infinity, y is vertical, and you actually applying it lambda, and this is the different, this is lambda, and this is the surface. This whole is a surface, and this is the scale of which is c. Okay, and normally it is represented at the scale or the whole cover area of the cover area of the body. So this is normally represented by C. So obviously the boundary layer is very less than whole of the shape of the body. That's understood. That's not a problem. But we have assumed this. We have to take this as an assumption. First of all, this is the basic assumption, and under this assumption, we're going to work out how we're going to reduce this equation to an approximate form, so that all the four equations which I have discussed earlier on, continuity, x momentum, y momentum, and energy, can be taken out by reducing this equation whole sort of. Let's see how we're going to do it. For example, the continuity equation is derivative of which is in terms of momentum. I will discuss it is density into u, and which is velocity. You have to multiply with density into velocity to get the momentum. So let's see, for example, it is rho. So it is the continuation equation, so which is equal to 0 when we're talking about in terms of non-dimensionalized variables defined. That would be a derivative of p prime u prime, derivative of x prime, and it is in terms of velocity v. We have taken in terms of velocity u, then and again in terms of velocity v. Is the adding up both is equal to 0, which is u prime is order of magnitude equal to 1. Order of magnitude equal to 1, and that is how you're going to represent it, is by 0 into 1, from 0 to 1, which is p dash is equal to 0 to 1. Also, since x varies from 0 to c, okay, normally that is a scale, so x prime will be also equal to 0 into 1. We have symbolized it when we're talking about the order of magnitude equal to 1. That is why it is an order of magnitude equal to 1. Okay, we've been talking about u prime and talking about p prime, and when also since x varies from 0 to c, so this is x prime. So y varies from 0 to lambda. Yes, that is along the y-axis. Since where lambda is very less than c, then y prime is of a smaller order of magnitude, denoted by y prime, which is equal to 0 and into lambda by c. That is how you're going to cover it up. Okay, so y prime is equal to 0 into lambda by c. This is how it has been covered. So to talk about the y-axis, we have talked about the velocity along the x-axis. We talked about the velocity along the y-axis, taking on the derivatives, and symbolizing in the order of 1. Okay, both the u and p, and we have represented along as y prime is also equal to 0, which is 0 lambda by c. So that is where then y prime is of smaller order of magnitude, denoted by, obviously lambda is very less than c. That is why the y prime which is along this lambda is also will be very less. So that is why y prime is equal to 0 into lambda by c, which is lambda as compared to the scale of the body. So without loss of generality, we can assume that c is a unit length. Okay, so y prime will be equal to O of lambda. That is how you're going to define the derivative of y in terms of lambda. That is understood, and we're going to place it 0 into 1, order of 1 multiplied by this, and then again we have to multiply by. We are actually placing the whole sort of the concept over here. Okay, just for this equation we have actually we have considered this one whole as order of 1, so that would be, yes, so that would be order of 1. Here it is not exactly, because we have to actually further apply this one. Let's see how we're going to do it. Okay, equation clearly v velocity must be an order of magnitude equal to lambda. Okay, that is v prime is equal to 0 of lambda. Okay, and now you're going to put on the equation. What we have done over here is this form. This is equal to order of 1, and we talk about this one, which is also of order of 1. Okay, because it is being discussed v prime in terms of y prime, and when we talk about this one, this one is also order of 1. Okay, so you multiply it by d over dy into mu of prime into rho v dash over rho derivative of v prime into our x, derivative of x prime in respect of v prime. So when we have taken this is also as the order of 1 magnitude. So let's see how it has been covered. This is actually d over dy is over here. Okay, so this whole lot has been covered, and this is how you're going to do it with 0 over into 1 over lambda square. And when adding on the value, putting in the value, basic equation was this first one. This, you put all the order of 1 values by taking out an equivalency. We just going to put on the values. We're going to have this form. Okay, because 1 by lambda one by lambda squared is from this, because this whole lot is 1 by lambda square. This has been represented by over here. Okay, 0 into 1 by lambda square. Real numbers is large. Okay, this one is a large number. That is talking about. So this would be equal to this. You have to consider this. I have to neglect this or ignore this because of this is very large number. Okay, adding a large number to a small number makes no sense. So that is why we have to ignore this one. And when going to add it like this, so this is the order of 1 into this. Okay, sorry, this is large. Okay, and when we are talking about the 1 over our real number is equal to 0 into lambda of square, so we are going to put this over here. So there, if the equation will become this one, and it will also become 0 into 1. The same over here, 0 into 1 over lambda squared. And putting and opening, obviously just substituting it with the original values, we have got this equation, and we are just going to have this one over here. Till here we have actually taken up the equation, and when we're going to again approximate it, and obviously you know that the whole process of this is the approximation. You need to the derivatives are also approximation. So approximating means that we're going to actually come back taking the first order derivative, and from that would be the basis of the approximation equations. Normally the equation that we mentioned over here, it is of first order, and it is the first order equation. That is why all the equations that we mentioned as 0 or 1 of order of magnitude equal to 1. So but obviously we normally start from order of magnitude equal to 0 as well. So over here we have to drop down again of order of 0, again approximating it again to 0. That is why it is known as the approximation technique. We have to take it again to 0 for that it tends to 0. So again this would be the form, and when we're going to take it again approximate with respect to an x, okay, and where x tends to 0. So that is why it has actually taken us to this equation, which is approximately x momentum equation. Okay, so when we're going to talk about which holds for flow in a thin boundary layer at a high Rayleigh numbers, obviously understandable. And then we have taken this. Okay, we have taken the first order, and that is the order of magnitude, replacing it for the y momentum. Y momentum obviously represented by lambda, so that is why we have represented over here by lambda, as we were discussing when we are taking this form, when we were talking about the lambda in as compared to velocity prime, when we're talking about v prime in terms of order of lambda. So here we have actually discussed that this form would be like this. Okay, so that would be order of magnitude, and that would be this one. So order of magnitude is this, and 1 minus rho m square into this one plus this. Again, coming back to that same order of lambda equation, and we have come across for that in terms of y momentum. Okay, x momentum was just coming from order of 1 back to the order of 0, and there we have got the x momentum. And in y momentum we have actually used order of 0, and we have moved towards the order of 1, but in terms of v prime, not in terms of u prime, and that is the difference. And when we talk about v, that we discussed about the lambda, and when we talk about u, we and when we talk about the u, it was in terms of, sorry, when we talked about the u, it was in terms of this assumption. Okay, it was in terms of x. That is why it is also in, that was in terms of x, that is also, that was on the boundary layer. So when we talk about u, we talk about x, but we talk about v, we're going to discuss in terms of lambda, and that is the difference, and that will create the y momentum. U, just by the letter u, both represent velocity, but talking about the momentum, obviously it is on the x-axis, on the y-axis, the two different momentums, so that is why it has been created. X-axis will create u velocity, and y-axis will create v velocity, but against lambda, and against x and against lambda, so, or y in other sense. But that is how you're going to explain it. That is over here, d rho v p prime over rho v dash is equal to this or smaller, assuming that r m lambda square is equal to 0 of 0 of order of 1. Since lambda is very small, you can say rho p prime is equal to rho p v y prime is very small. Y momentum equation. So specialized to a boundary layer, there we got the y momentum equation, that is rho p over rho y is equal to 0. There we got the y momentum layer. So boundary layer is equal to p is equal to p of rho of x and equal to rho e into x. So that is how we got the y momentum. This will help us to generate the y momentum, because this is very small. So the whole concept over here will tend to be very small. Okay, and we're just going to be left alone only by this one which is rho p over rho y, and that whole equation is equal to 0. The rest of the one wouldn't be neglected. Okay, and when we talk about an order of lambda, because all are very small, so we have to ignore assuming that r into this one m lambda square is equal to order of 1. So lambda is very small. Because of lambda is very small, that is why we have to ignore all where it is lambda or order of lambda. We have to ignore them, just actually keeping it over as simple as that. This equation would be left. And we talk about in terms of y momentum, you just have to consider all the other, because when we talk about the v, we talk about lambda, and lambda is very small, so we have to ignore it. So that we got it. Energy equation will be represented, and we just have to replace it by h. Okay, wherever there is you can say v has been replaced by h, and over here, that is the basic equation. Let me actually go back to the basic equation. uv, so u obviously has been replaced by the equation, and we have also replaced it by, so this equation has been replaced for just for the energy purposes, or the energy equation. This h has been substituted, and also we have placed in the k as well, and all the equation is all the same. And just to see that continuity is this. Okay, derivative of rho of u and derivative of rho of v, just adding both is equal to 0. X momentum is rho u into derivative of u into x, rho v derivative of u into y. Okay, and we have got this one as well. So this is for the x momentum. We have already discussed it in detail. This is for y momentum. We have already discussed this in this energy equation when we talk about h and k. Okay, so boundary conditions. What are the boundary conditions? At wall, y is equal to 0, velocity u will be equal to 0, v equal to 0. So this would be t is equal to TW. Okay, that will be temperature at the wall. Okay, at boundary layer edge, y is tend to infinity. Okay, and u also will tends to u of e, and temperature will tends to t of e. Okay, so note that since the boundary layer thickness is not known a priority, the boundary condition at the edge of the boundary is given at large y. Essentially, y is equal to infinity. Okay, you need to consider that the boundary condition at the edge of the boundary is given at large y. So this is how it has been done, and I hope so that with the help of this, what we have learned that obviously just putting it in an awkward position right now. The whole video was in an awkward position, just apologizing that for that reason. But we have learned the equations, the boundary layer equations. We have learned in the terms of the equations which are continuity, x momentum, y momentum, and energy. We can use these equations to put in to solve out the problems, but we have actually taken some of the concept from where we have extracted those videos with the help of the derivatives, but taking this form of the equation, because this equation what has been driven from some of the earlier chapters, because this chapter is obviously at the last of the book, but the basis of this equation has been explained in the textbook. In the previous chapter, we'll try to cover what will be the basis of this equation with the help of different concepts and different vectors, different concepts, different sort of the techniques, so that we can see how we reached this form, the equation, which will help us actually get the boundary layer equations as well. But that is another separate video section, I believe, and we have to cover separate a couple of videos, a couple of more videos, so that we can cover this concept as well. But right now, this equation forms the basis. We have taken the assumption that lambda, which is the boundary layer is very small as compared to the scale of the body. Understandable. We have taken lambda in terms of y, and we have lambda in terms of y, and when we talk about y, we have talked about v as well. When we talking about x, that is x-axis, we have talked about u, which is the velocity. Just multiplying rho into density into velocity, we get the momentum. We have talked about the x momentum. We talked about the y momentum by taking out the first order derivative. Yet again, moving up this is the approximation technique. So the first order derivative will be converted into the zero order derivative, and the zero order derivative will be solved out to get the boundary layer equations normally, because the boundary layer is very thin, and we have to use the approximation technique as we have earlier used in some of the other videos, and as I discussed earlier in the same video as well. So I hope that with the help of these equations, with the help of these concepts, we've taken out the continuity equation, x momentum, y momentum, energy, all from the basis of the first equation that we have actually noted down, and just doing out some of the derivatives just from the first order to zero order, and from zero order to first order. And when talking about the y momentum, and energy is in front of us, just replacing it by h and replacing it by our k, just doing it, and we just have that equation as well. We can actually multiply it, so we get all sort of the equations. So the conditions are in front of us. We want to have the condition at wall, we have to get the condition at the boundary layer edge as well. So these conditions needs to be met. Obviously, that is why we have taken this approximation technique, so that we can find out the best of the best actually equations for the boundary layer. So I'm going to end up my video over here. I have actually explained you enough, but there is another section of numericals. There will be another sections of problems, another subsection of theoreticals and learning that will help us to actually gain more and more, so that we can extract as much possible from our lectures and videos. So I hope to see you with some another interesting video with another interesting aerodynamic concept, aerodynamic techniques. This is the foundation of courses that we're going to cover later as semester per semester, covered by different institute in IIT institutes, whether it is Kanpur, whether it is Madras, and whether it is Bombay, whether it is actually some of the other IIT institutes are concerned. All over the country, we're going to cover the different courses, different concepts, just remaining within the domain of aerodynamics, aerospace, and nautical engineering, further extended to chemical engineering, mechanical engineering, and also to the structural engineering, so that it may help us to cover eventually electronics as well, and also the computer engineering as well. But those would be under the paradigm of aerodynamics and aeronautical or aerospace engineering. We're going to see you soon with some another interesting video, and I hope that you're going to like our content, and if not, please keep watching, suggest us more methods, let us know about how we're going to improve ourselves in terms of video making, in terms of delivering out the lectures, or if there's some sort of a mistake, there's some sort of error, please point out so that we can rectify those errors for our future references, and also for future videos, and also for this platform as well. So I hope that you're going to subscribe, and do share, like, and comment. We're going to wait for that. Until the next video, take care and have a nice day.